MPLS, or the multi-protocol label switching. Now, MPLS is one of those technologies that is really a service provider technology. It is used by some enterprises and used very successfully by those enterprises. Sometimes it's just a way of replacing older ways of connecting their branch offices, like for example replacing ATM circuits or replacing frame relay circuits or dedicated serial lines. But sometimes it is actually used by the enterprises inside the enterprise to make a separation of traffic between different business units or anything of the sort, so using MPLS VPNs. Now, when it comes to the CCIE routing and switching exam, the scope of MPLS there is rather unusual because it doesn't really fit into either one of these categories. It's not actually going to be tested at what would be considered the quotes service provider grade MPLS implementation, but it wouldn't actually be the vanilla use that you would find in MPLS environments. It's going to be something in between. So in order to actually go through the MPLS at the level that is relevant for you for the CCIE routing and switching test, what we are going to do here is we're going to divide talking about MPLS into two separate categories. We are going to talk about MPLS infrastructure and then we are going to talk about the MPLS applications. And here I should just say MPLS application because the only MPLS application that you actually care about is layer 3 VPNs. Now there are other MPLS applications like for example MPLS traffic engineering or layer 2 VPNs that you don't really care about that you don't really care about for the CCIE routing and switching test because these technologies are not tested in the exam. What is tested is layer 3 VPNs, and you need to understand how layer 3 VPNs operate, but also you need to know how to build a good, successful MPLS infrastructure. So to do that, let's start with just MPLS infrastructure. Now, MPLS infrastructure, when it comes to this class, and this is going to be very, very, very Cisco iOS based. So some of the things that I will be saying and talking about now are not necessarily applicable to other vendors or other implementations of MPLS, like for example on Alcatel-Lucent equipment or on Juniper equipment, because their approach to MPLS is slightly different than Cisco's. Cisco's approach in iOS is that they wanted to make MPLS really, really easy and accessible. Now, I know that sometimes MPLS and easy don't actually go well in the same sentence, but trust me when I say, and I don't really have too much behind me other than my two CCIEs, that MPLS is really relatively easy technology. It's much, much simpler than OSPF. It's much, much simpler than BGP is. It's actually relatively simple technology. Now, another simple technology that we have available to us is this. This is just a pen. Now, if I gave you this pen and I ask you to draw me a Mona Lisa, how many of you would actually be able to do that? Not many, but this is also what MPLS does. MPLS in itself is a simple technology, but what you can actually do with this technology is rather complex and complicated. So MPLS itself is not that complex. It's the MPLS applications that add the complexity there. So we're going to talk about MPLS applications later on, but right now I want you to have this in mind that iOS really tries, or Cisco with Cisco iOS is trying to make MPLS rather easy. Now, how did they approach MPLS in iOS? Well, first things first is MPLS is globally enabled on all Cisco routers. Now, what I mean by MPLS is globally enabled, I mean that MPLS is there, all the functions of MPLS are ready to start working the moment you enable MPLS on any of the interfaces. Now, MPLS, or the label switching, is not enabled on any interfaces by default. So all these things are actually, what these things are, I will talk about in great detail, but all these things are actually in standby there. They are waiting to be turned on, and the moment you enable MPLS on one interface, a whole set of things happens behind the curtains without you actually having to do anything, because MPLS is right there, it's globally enabled and ready to go. Another thing is that MPLS is supported on almost all Cisco routers. So you will be hard-pressed now to actually find a Cisco router. Now, this is not necessarily true for switches. You will be hard-pressed to actually find Cisco routers these days that don't support MPLS. Now, and by Cisco routers here, I don't mean, really, really low-end consumer-level devices that Cisco used to have. Like for example, of course, you're not going to see MPLS on Linksys, but by the way, I don't think that Linksys is part of Cisco anymore, but you are going to see it even on the smallest, let's say 800 or the 900 series routers. It's there, it exists. And another thing is that by default, MPLS traffic, when enabled, will follow the same path as regular IP traffic would. Now, this is the important thing. This allows MPLS to be enabled in the network without causing a major disruptive event. Now, I'm not saying that you can now go to your production network and turn MPLS everywhere and that everything will be working fine. Now, I can say that with high degree of certainty that would be the case, but there are certain things that can still go wrong in MPLS that are not necessarily happening in the IP world that can cause your traffic to actually be black holed, dropped, and not actually work. So this is not a blank check to go out there and just turn on MPLS everywhere, but it is easy. You could do that, and in vast majority of cases, unless you're doing a couple of special things in your network, you are probably going to be fine. I'm saying probably, so don't go ahead and do it in your production network, but you could theoretically do that. In theory, there is no difference between practice and theory. And another thing is, by default, again, so I'm just going to say by default, all IGP routes will have a label assigned. So all IGP routes, and I should clarify here that by IGP, I actually mean IGP routes, connected routes, and static routes. So all these routes from these sources will actually have a label assigned by default, so you don't actually have to do anything. So this is what makes MPLS easier and more accessible in iOS. Now, with other vendors, this is not necessarily true. With other vendors, you may actually have to do a little bit more work to get MPLS up and running. With iOS, all these things are actually there by default. So let's first see another thing about the MPLS. To understand and fundamentally get MPLS, we have to understand that MPLS actually consists of two related but relatively independent operations. And this is the MPLS data plane and MPLS control plane. Now, the data plane basically deals with how MPLS traffic is forwarded in, out, and through the MPLS network. So data plane deals with the actual traffic. Control plane in MPLS deals with how the labels are assigned and exchanged in the MPLS network. So these are the two, as I said, related but relatively independent operations of the MPLS. And I would have to explain one or the other, but again, this is a situation where we have a little bit of a chicken and the egg case. So I can explain the data plane, but then we would have to assume that the control plane worked properly. I could explain the control plane, but then certain aspects of the data plane would come into play and they would make no sense without actually understanding how the data plane works. So the first thing that I'm going to talk about is going to be MPLS data plane. And I'm going to work under the assumption here that the control plane works. So this is the assumption here. So I'm going to explain this with a thought that, okay, the control plane exists, the control plane did its job, whatever its job might be. I'm going to explain that in a moment, but this is how the data plane is going to operate when the control plane actually operates properly. So let's say that we have a network that consists of several routers. So I'm going to have, let's say 4 routers. That should be more than enough. So let's say that this is R1, that this is R2, that this is R3, that this is R4. So these routers here are going to be in our MPLS network, and then I'm going to have 2 nodes, let's say A and B here, that are outside of the MPLS network. So this here is the boundary of my MPLS network. So what I have here below is MPLS, and here above I have just a regular IP network. So the same thing here. This is where the IP network here is, and this is where my MPLS network is. Let me just move this slightly to the side here. Now, this is the setup, and this is the network where I'm going to try to explain MPLS. So let me just move this up a little bit. Also, what I'm going to be looking at is only what happens when A wants to communicate with B. So this is the way my traffic will be flowing. So I want to see what is happening with this traffic, what are my routers R1, R2, R3, and R4 going to be doing in this case, and how this MPLS traffic, or how this IP traffic from one side is going to go through the MPLS cloud, how is it going to go through the MPLS backbone, and how is it going to reach B. So let's say here, as a start, that my router A here sends just a regular IP packet. So this is our IP packet. Now, this IP packet is sent, and the destination IP address of the packet is going to be B. So this is what exists on this IP packet. When this IP packet arrives here to R1, it is going to be just a regular IP packet. So A is an IP node, and R1 is the first node that sits on the MPLS network. Now, because it is sitting at the edge of the network, this is going to be called an edge node. Now, in MPLS, all the routers are called LSRs. LSR stands for Label Switching Router. So R1 is going to be edge LSR, and R4 here is also going to be edge LSR. Why is it going to be edge? Because it sits on this border between the regular IP network and the MPLS network. Furthermore, to be more specific, R1 is actually called, in this scenario, ingress edge LSR, and our R4 is called egress edge LSR. when an IP packet arrives to ingress edge LSR, this ingress edge LSR needs to perform a lookup in a table that we call LFIB. Now, LFIB stands for Label Forwarding Information Base. And in this LFIB, it needs to see what information, what does it do with this packet. So what we might have in this LFIB is information that incoming packet with the destination of B needs to be sent to R2 out of interface 1. Let's say that this is interface 1, that this is interface 0. Let's have that on all the routers. That this traffic must be sent out of interface 1 with the label, let's say 53. Okay? So now, when this IP packet here arrives, we are performing an LFIB lookup and we say, oh, okay, destination IP address is B. That means that in the LFIB, we are looking for B and it says, okay, send it to R2 out of interface 1. That means it will be sent out of this interface and use label 53. So what we are going to have now is an IP packet that goes here and that gets installed a label from the LFIB 53. So we get this label 53 installed on this packet. Now, this packet with the label arrives to R2. R2 is just a label switching router. It is now receiving a packet with the label 53, and it's now looking up in its own LFIB. It's looking for entry that says, what should I do with the incoming label 53? Now, let's say that in its own LFIB, R2 has information that 53 needs to be sent to R3 out of interface number 1 with the label 71. So now, what R2 is going to do, it's going to take this packet, it is actually going to drop the label, it's going to throw the label 53 out, so 53 gets dropped, and this label 71 now gets installed in the packet instead. So this packet now gets the label 71. Now, similar thing is going to happen on R3. R3 is now going to have entry in its own LFIB that says 71 needs to be sent to R4 out of interface number 1, which with, let's say, label number 3. So this packet now arrives to R4 and arrives to R3. So what happens on R3 is we are going to drop this label 71. We are getting rid of it. And instead, we are going to install label 3 on the packet. And then we are going to forward this packet to R4. But take a look. R4 here needs to send this to B without the label. So in its FIB, in its LFIB here, it is going to have an information, and I'm going to put this in parentheses. It's going to have an information that incoming label 3 means send traffic directly to B out of interface 1 and don't use any label. Okay? I'm putting this in parentheses for a reason. So I'm just going to somehow highlight these parentheses because the reason for this will become apparent a little bit later on. So here I'm going to have this packet that is now sent here. So what is happening here? Basically, we have now information that this label 3 needs to be dropped out of the packet, and then we actually need to perform an IP lookup what to do with this packet. And here we have information that B is directly connected route, for example, and only then we can basically send the packet out. So at this point here, at the point of R4, we are doing two operations. Sorry, maybe you're not actually seeing this, so let me just do this. So we have two operations. One operation is label lookup, and the other operation is IP lookup. So this is not exactly the most optimal configuration of it all. So this is not the best thing. These two operations are suboptimal. So in order to understand what actually happens by default in Cisco routers, let's give these different operations a name. So this operation of actually taking a packet that did not have the label and installing the label on the packet is something that is called MPLS push operation. So this is where we say that we are actually pushing the label onto the stack. This operation here, where we took one label out and we replaced it with another label, is something that we call the swap operation. The similar thing happened here, and I'm going to put an asterisk here because, as I said, this is not exactly what happens, but I'm trying to explain or make you understand why this is not the way it works. And finally, this label operation here, where we actually removed label from the packet, is something that we call pop operation. So when it comes to MPLS label operations, we basically have the following operations. We have push, we have swap, we have pop, and there is one more that I haven't shown you, which is delete. Now, let me explain these very briefly. Label is installed on the packet. Technically speaking, what this is called with the proper terminology is label is pushed onto the stack. And what this actually means will become a little bit clearer later on. Label is swapped, and I will be more specific here and say topmost label is swapped. And again, what this means here will become a little bit clear later on. Pop topmost label is removed from the stack. And again, I will explain why this is significant. Now, delete operation, and I'm going to write this is red. Entire label stack is destroyed on the packet. This is an extremely dangerous operation, but again, this is something that at this moment in time when I'm explaining MPLS is not that significant, but it is very, very important when you start working with MPLS VPNs, because when you have a delete operation, you are going to have a serious issue with your MPLS VPN reachability. Again, I will explain what this pushed onto the stack, pop from the stack, or topmost label means, but at this point here, those terms may not make much sense, but this is what the operations do. And this is in really the simplest form. Push operation simply means when you have an IP packet, just add the label on it. Don't remove anything from it, just add this label onto the packet. Now, what swap means is take the label from the packet and put a new one there. That's it. What pop means is just remove the label, throw it away, and send the packet. Whatever remains in the packet, just send it out where it needs to go. Now, if it's an IP packet, when you popped the label, if what remains is an IP packet, we may need to perform an IP lookup to actually successfully send this packet out. Now, if you need to perform an IP lookup and the POP operation on the same device, this is not a very optimal situation. So this is why another concept in MPLS exists, which is called penultimate hop popping. So here, that's one thing that I will explain. So penultimate hop popping operates in the following manner. So let me delete this part here. Because it is not entirely correct. Now, penultimate hop popping, so let me just add that somewhere. Or actually, I should put the dash. It's penultimate hop popping. And I just have to say this again, penultimate hop popping. It just has such a great name. Also known as PHP, not to be mixed with the programming language called professional home pages, or that was the old name, now it's just PHP. But this is the concept in MPLS where R4 here, instead of doing these two operations, instead of doing the label pop and then IP lookup, can actually request from R3 to perform the pop for it instead. Now, this is going to be signaled using a special label, which is called a null label. So R4 here is going to communicate for this prefix a special label called implicit null. So let me just write it down. So implicit null label. Now, implicit null label has value of 3. So when we have this implicit null label, what's going to happen here on R3 is the exact thing that we had before. This incoming packet that had label 71 is going to arrive to R3, and we're going to see that for 71, we need to send this to R4 out of interface 1, and the label assigned here was 3, our implicit null label. So we are going to drop label 71 and send actually just an IP packet. Instead of adding any labels, instead of actually adding 3, we are going to send just a regular IP packet. So basically what we are doing here at this point is we are doing a pop operation. Now this pop operation is actually a penultimate hop popping. So we can say that this that happened here was actually a PHP operation. But technically speaking, it's just a pop operation that happens one hop before where the pop would actually happen. So it's not the egress edge LSR that will be doing it, but it will be penultimate hop. So this will be the ultimate hop, and this is penultimate hop, one before the last. So with this PHP, what is now going to happen is that this packet is going to arrive as the clear IP packet, as a regular IP packet to R4, which means that R4 now can, instead of performing 2 operations, can just do the IP lookup instead. So here we are just going to add an IP lookup on the packet, and this packet can now be sent towards its destination B without actually having the label. Just what we wanted, except that we didn't have to perform 2 operations on R4. This functionality, PHP, is automatically enabled in Cisco routers, and this is not exactly how it works, so let me put that warning. So this is not how it works, and see PHP later on. So this is basically a warning that this is not exactly how it works, but in order to understand why it works the way it does, we actually needed to go through that exercise to see what the problem with that approach is. The question that I'm getting is, if on R4 we configure explicit null, and this is something that can be done on Cisco routers, are you disabling PHP? Well, yes, this is what should happen, but you should it's not actually going to work the way you expect it to work, because it is going to be used only in specific cases. Mostly when you have MPLS VPNs and mostly when you have carrier supporting carrier scenarios. For regular MPLS VPN, first of all, you would, for regular MPLS without the VPNs, there would be absolutely no need for you to ever turn on the explicit null. And even in iOS, and I've seen this now, I haven't tested it recently, I have to admit, but in some of the older versions of the iOS, even if you enabled the explicit null, you wouldn't actually turn off the penultimate hop popping, because the iOS on R3 here would say, okay, how many labels do I have on the stack? If it's only one label on the stack, it would actually pop it, perform PHP, even though R4 expected to have PHP disabled. So I had mixed success with actually turning off PHP. But in some other scenarios, you actually have to do it. But this is not something that you will encounter as a question in the lab. We can test it on later on if you like, but theoretically speaking, yes, when you enable explicit null as the idea, that is, that instead of sending label with value 3 here, we are actually sending the label that indicates that it's a null label. And it's not 0, but I actually forgot which value it is. If you are sending the explicit null, that should signal R3 to turn off PHP, but I had, as I said, mixed success in making it work. Another question that I'm reading here, it says, and I'm just going to read it entirely, it says, my understanding was that LSR sending traffic to an edge LSR actually sent a final label, 3 in our example, but marked the S bit so the edge LSR would know how to remove the label. Is this incorrect? Technically speaking, yes, it is incorrect. Now, the S bit in the MPLS label is something that stands for bottom of the stack label. Now, bottom of the stack label will always be set to 1 on the label that is closest to the payload. So there are cases when you are going to have more than one label on the MPLS packet. I wanted to talk about this later on, but anyways, let's do it now. So let's say that this is the regular IP packet. From MPLS perspective, this is payload. Now, why is this payload? Because the payload in MPLS could be other things. It's not necessarily just IP. This is why it's called multi-protocol, because it can carry multiple protocols. So what happens then is here we are going to add the label, and here we are going to have the layer 2 headers. So whatever layer 2 technology we are using. Now, if you want to use multiple labels, basically what's going to happen is that you are going to have another label here and another label here. And as many labels that you actually want to have. Now, the point here is that you are, in most cases, going to see just 2 labels for most of MPLS applications, but there are scenarios when you're going to have 3 or 4 labels on the stack. Granted, those are very, very special cases. Like, for example, when you have an MPLS VPN and the VPN customer that you are actually connecting to is another ISP, so this is a carrier supporting carrier scenario, who has their own MPLS VPN. In that case, you might actually have 2 labels. Then in your network, you might be using MPLS traffic engineering, so that you might have an additional tunnel on top of the regular traffic that adds 1 more label. And let's say that that tunnel was protected by something that is called MPLS fast reroute, which got activated, so you need to add yet another label on that stack. So there we go, you have 4 labels on the stack. But those are very, very special cases. But in any case, MPLS supports this adding the labels on the IP packet or on the payload, and this is why we basically call this the label stack. So this is the label stack. Now, this label here, so let's take a look at the label. The label basically consists, now I'm probably going to get the order of these fields wrong, so don't hold it against me if it's not really, really correct in the order. I think I will get it right, but I might get it wrong. So the first part, I think it's the first part. I'm sure about the sizes of these fields, but I'm not entirely sure about the order in which they appear. And then we have, so this is 24 and 8. So we're going to have 20 bits that are the actual label value. We are going to have 1 bit, which is this S bit. Then we are going to have 3 bits that are experimental bits. And then we are going to have 8 bits that are time to live. Now, this S bit is always going to be set here. So this one here will have the S bit set. No matter how many labels you have onto the stack, the bottommost label will have S bit set to 1. Now, what this S bit tells the router when the router receives it, and in this case, it will be router R4, it tells it that after you pop this label, after you remove this label, you actually need to perform an additional operation. You need to know what the payload is and what to actually do with the payload. So if it's an IP traffic, we may need to perform an IP lookup. If it's a layer 2 end-to-end traffic, if you're using a layer 2 VPN, you need to forward this traffic based on your layer 2 forwarding operations. If it was something else, like for example TDM over MPLS, which actually exists, you might need to do the operation that relates to that particular operation. So this bottom of the stack bit signals, in our case R4, if it received that label. So in this case here, it signaled R4 that it actually needs to perform this additional operation. Now, the point is that when you are using penultimate hop popping, you are not going to have the S bit set. Why? Because the packet that you are actually receiving doesn't have a label. It's just a regular IP packet. So you are not going to have the label with the S bit set. Now, if you are using explicit null label, what is happening in the explicit null is that this value here, may indicate that it is an explicit null. So this can be either some number value, it can be explicit null value, or it can be implicit null value. It can be a couple of others, but these are the implicit, sorry, I just wrote the wrong thing there. So implicit null. So if you have this, if you have the label, you will have the bottom of the stack bit. So in that case, that would have been correct, that when the router sent the bottom of the stack bit, signal the other router that it needs to pop the label. But that's what bottom of the stack bit does anyways. It tells the router that after you have popped this label, you may need to perform an additional operation. And now, while I'm on the subject of looking at the actual packet here, when we have a label stack like this, this label here is the label that we call the topmost label. So all the pop, push, and swap operations deal with only this label. But if we had a delete operation here, delete operation would actually be working on this whole stack here. So if the router was instructed to delete the label, it would remove all these labels. But pop operation will just pop this one. Push operation would just add the label to the stack, and swap operation would just take this label and put the new one in, with these two here being completely intact.